Okay, now let us discuss the implementation of neighbor lists in the code. Okay. So, what do we have to identify? We have to identify the neighbors. What are neighbors? So, all the particles, the ns particles which are within distance rs of particle I. So, they are the neighbors. So, we have to identify them and store them in an array. Now, for the neighbor list, to make a neighbor list, you need actually two arrays. Okay. One array will store for each particle I. So, I runs from 1 to n part. So, the length of this array will be n part. So, you initialize an array, suppose no neighbor means number of neighbors of length n part, where n part is essentially the number of particles in the box, which we call n when we discuss. But in the code you should have a bigger name like n part, n number of particles. If you write n, n is often used as a dummy index in do loops, right. So, that is not a good name. So, that is why in the code you could write n part, and that is equal to n, the number of particles in the box, and you have to have an array, suppose number of neighbors, which says for each particle, particle 1, 2, 3, how many neighbors does particle 1 have. Suppose particle number has 5 neighbors, particle number 2 has 7 neighbors, particle number 3 suppose has 2 neighbors, which means you have 2 particles. Suppose particle number 3 is I is 3, suppose this I is 3, and then particle number 3 has 2 particles within distance r s. So, if you draw around the position of particle number 3 a sphere of radius r s, then the number of particles, neighboring particles which are within distance r s of the position of 3 is 2, and that is what 5 means. It means there are 5 particles. So, n is equal to 5 for when I equal to 1, right. So, you need one array number of neighbors which stores the number of neighbors of each particle. Number of particles in the system is n part. So, that is why its length is n part, and then the index of the neighbors is stored in another array called NEI list, NEI for like neighbor list, NEI list, which will be a 2-dimensional array of length n part. Okay, the number for each particle you have to identify which other particles are its neighbors. So, n part one size, so on one side it will be n part, and on the other side it is max number of neighbors. What is max neighbor? It is the maximum number of neighbors that any particle could have. Okay. Why max neighbor? Now, suppose you have Lennard-Jones interaction, right, at a particular temperature. So, there are attractive interactions. So, suppose at a certain point in space you form a cluster of particles, cluster of Lennard-Jones particles. So, locally it is a very dense system, some other part it is relatively less dense. Okay. So, there can be density fluctuations because of interactions, not that the entire box will be uniformly filled with Lennard-Jones particles, right, because there would be attractions which could cluster particles. So, you need an estimate of what could be the maximum number of neighbors, right. Now, suppose you have an estimate, and how to estimate we will discuss this soon. Then basically you say okay, particle number 1 has 5 neighbors which might be say 23, 99, 301, 899. So, these are the 5 neighbors, and rest of the array will be 0, right. Now, particle number 2 has suppose 7 neighbors. So, NEI list this array which is a 2-dimensional array, particle number 2 will have 7 neighbors say, and what are the indices of those neighbors, the identification of the neighbors, suppose particle number 55, 203, 365, 623 and so on and so forth. So, there are 7 neighbors, rest of the array is 0. Now, suppose particle number 3 has 2 neighbors say, they may be 7 and 24 say, rest of the row is full of zeros, right, and so on and so forth for each particle. So, for each particle you basically save the number of neighbors in this array, and you use this array when you have to calculate force, because now you have a smaller list of neighbors for each particle. So, for each particle you do not have to check over n number of particles in the box. You now just have to check over only this small set of particles ns for each of these particles, and you calculate the distance, and if the distance is less than RC. So, this so basically ns here would be 5, 7, 2, 8 for different values of I, and now you calculate. So, over the next 100 iterations you calculate that how many of these particles are within, so how many of these neighbors for a particular particle I is within RC, and then you calculate the forces. What are you saving? You are not checking over all the particles, and every 100 iterations, since the particles would have moved. So, if suppose particle number 3, and so around particle number 3, 7 is within RC at time t equal to 0. After the particles have moved, 3 has moved, 7 have moved, after say 70 iterations, it is possible that particle number 7 is no longer within a distance of RC of particle number 3, maybe particle number 24 becomes at a distance less than RC from the current position of particle number 3, right. And after 100 iterations, when you update neighbor list, of course, this all these these will be rewritten, and you have to write the current after 100 iterations, the current at that time the neighbors. You have to make a list of neighbors which will be the neighbors of each of these particles. Okay. So, that is the broad idea. Okay. So, how do you estimate max neighbor, right? Now, so that is discussed here. So, how would you have an estimate of max neighbor? Basically, n by L cube, n is the total number of particles in the box, and L cube is the volume of the box. So, n by L cube is essentially the number density. In a unit volume, how many particles do you have? That is what is number density, right, n by L cube. And if you multiply it by m, then you would have the actual density, right, mass of that entire system divided by volume, that is the density. N by L cube is the number density. N by L cube is the number density into 4 pi by 3 R s cube is the average number of particles you would expect in a sphere of radius R s, right. But as I said, I mean due to interactions, local density within a certain part of the box could be much higher, could be 3 times or 4 times that of the average density, right, and some other part of the box could have lower density. So, you would typically choose max neighbor, max neighbor, so this quantity as 4 or 5 times this number. So, this is the total number of particles within this box. You can choose it 4 or 5 times more, and I mean even if there is some inhomogeneity, you would not expect larger deviations, but that is not impossible. And if you indeed have larger number of neighbors than you estimated initially by max neighbor, then when you calculate neighbor list, the program will show an error, and then you must check whether basically for a particular particle in the neighbor list, the number of neighbors that you have for that particle increase is more than max neighbor, then you have to basically change the value of max neighbor to a higher value. There is no point in giving it too high a value, because then this array will become too large, and if you have to handle large arrays, the code becomes slow, okay, because it takes time for we will discuss this later, why the code becomes slow if you have large arrays. But of course, if you have n part particles, then you do have some large arrays like position, velocity, which is 3 into n part, velocity is 3 into n part, then the force array and the old force array, each of these are 3 into n part. But here this one, which is a 2-dimensional array, is typically often the largest array in the standard MD simulation, because of the large value of max n bar. Okay. So, that is basically the broad idea how neighbor lists generated. Now, let us go into the details and discuss in even greater detail the algorithm, how when you calculate it in the code, what changes do you have to make from whatever we have discussed till previously. And so, now we are trying to increase the efficiency of the code, and believe me, without neighbor list you can hardly do any molecular dynamics simulations. As soon as the number of particles goes above 1000, you need neighbor lists, right. And typically you do molecular dynamics with 10,000, 15,000, depends upon the complexity of the interaction, the length of the iteration. So, these decide how many particles you have. You can even have up to million particles or 10 million particles interacting with each other. It depends upon your computational resources. Right. Now, let us talk about the details of how to create a neighbor list. As soon as you have more than 1000 particles, neighbor list becomes imperative. And suppose you have you are calling the neighbor list, you are updating the neighbor list every 100 iterations, right. So, where at what point in the code should you call neighbor list? So, here I have given a schematic, the flow chart or the schematic of the code. So, when you have your molecular dynamics code, at the beginning of course, you have your initialization, you define all the variables, and then initialize position, initialize velocity, calc force, and this is the main body of the code, where you have basically do I being a dummy variable, equal to 1 to number of iterations, depends how long you want to run the code, which in turn depends upon what quantity you are calculating. Then what is there in a standard MD? You have call update pos, means updates the position, then you store the forces into an array called the old force, then you calculate the new force in this step, right, and then you update the velocity. So, this is your main molecular dynamics code: update position, calculate new forces, update velocity, right. Then what do? Suppose you want to call the thermostat, right. You call the thermostat, suppose every 250 iterations, suppose, I mean you can call it 100 iterations, you can call it 50 iterations, but just for the sake of it, suppose you want to call the thermostat every 250 iterations, then you write if mod II equal to 250 equal to 0, mod essentially gives the remainder when you divide II by 250, and if that remainder is equal to 0, then call thermostat, which means the thermostat will be called every 250 iterations. If mod II comma 100 equal to 0, call neighbor list, call the neighbor list every 100 iterations, right. Then suppose every 50 iterations you want to call the subroutine, which will calculate your statistical quantities from a particular microstate. Of course, you have to calculate average over these statistical quantities over many microstates to get your thermodynamic average. So, you could be calling that every 50 iterations say, and suppose every 1000 iterations here in this step, you could call a subroutine which will write down the positions of all the particles on the computer. So, if you have the position of all the particles every 1000 iterations, you can essentially join them up and make a movie of your moving particles. You can visualize how your particles are moving, whether they are formed clusters, whether they are breaking up, whether they are moving, whatever they if you want to see a movie, that is how you make it. Okay. So, but now we are discussing neighbor list, and basically every 100 steps iterations you are calling the neighbor list. What will be there in the subroutine neighbor list? Of course, you have to start with subroutine nei list, nei for neighbor, underscore list, implicit none, and of course, this is the end of the code, end subroutine nei list. Here you have to define all your variables, whatever internal variables you need, but most importantly for the neighbor list, what you need to define is number of neighbors, this entire array, right, which stores how many neighbors each particle I has, 1, 2, 3, 4, how many neighbors each of these particles has, that you set to 0, and then array list which says the name of the subroutine, and this array has become the same. Just so what you could do is just call this suppose NEIGHBOURS 1 and this is NEIGHBOURS 1, never mind. So, this array NEIGHBOURS you have to set it to 0. So, in this array you store the indices, the number, the identification of the neighbors for each particle, right. So, that you set to 0. Then the loop goes like this, suppose do I j equal to 1 to n part minus 1. So, basically nearly all the particles, do j k equal to I j plus 1, I j is this, I j plus, just one second, I j plus 1 comma n part. So, that you are checking over each pair of particles in the system. When you are calculating neighbor list, you have to check over each pair of particles in the system. Now, basically I j is one particle, j k is the index of another particle. You calculate the distance, displacement dx, difference in positions in the x direction, in the y direction, in the z direction. Use nearest image convention to find out the smallest distance in each direction, then calculate r, the distance, the scalar distance between two particles, which is nothing but dx square plus dy square plus dz square, d square root before that. And if this r, if the distance between particle I j and if particle I j and j k is less than r s, then you say okay, the number of neighbors of I j is incremented by 1 in this step. So, number of neighbors of I j is number of neighbors I j plus 1. So, previously if it had 0 number of neighbors, then it says that okay, it has now 1 neighbors. Now, as j k keeps on changing and for all the values of j k for which r is less than r s, this the number of neighbors will be incremented 1, 2, 3, 4, 5, 6 up till say 7, right. And what does this array store? This step, it says that for particle I j, right, particle I j, the jth neighbor. So, see here you have incremented how many neighbors it has. So, that number equal to the particle index number, the neighbor index number, right. So, if this distance is less than r s, then in this array, you say that okay, the fifth neighbor. So, this is the fifth neighbor or the second neighbor of particle number I j is particle index j k, right, j k you are running over n part, and that is all that is there to it. Once this loop is completed, every 100 iterations, you will have these two arrays which constitute your neighbor list. It says each particle, how many neighbors each particle has, which is in this array, and what is the particle index of each of these neighbors of particle I j, that is stored in NEIGHBOURS list. Okay. So, now you have your neighbor list, very good. Now, how do you use it? So, the way you use it is you have to use this neighbor list in subroutine calc force, right. Previously in calc force you were checking for every pair of particle if the distance is less than r c, and only then were you calculating, the force, right. Here now this n into n part calculation, n into n minus 1 by 2 calculation is being done here in this naive list, which is being called every 100 iterations. And in the calc force, in the subroutine calculation of forces, what do? You say, okay, do I equal to 1 to n part minus 1, because you want to calculate the force on each particle, y n part minus 1, because the last particle has to have some neighbor, and that will already be calculated. When you calculate force, you just do it once, right. If some force is acted on particle j and equal and opposite force is being acted on particle I, right. So, you do not need to calculate it twice. So, do I equal to 1 comma n part minus 1, do j equal to 1 to number of neighbors of I, right. Then P, in this step you are identifying which particle number P is naive list I j. So, j is the so first neighbor, second neighbor. So, basically j changes from first neighbor, second neighbor, third neighbor, fourth neighbor, fifth neighbor, seventh neighbor, whatever. So, this P is basically the jth neighbor of particle number I, which is within distance r s, right. Then what? Then you calculate the distance dx, position 3 p minus 2, because p is the one, p is the particle index with which I is interacting. So, 3 p minus 2 minus position 3 I minus 2. Similarly, you calculate for dy, and similarly you calculate for dz, position 3 into p minus position 3 into I. Do PBC, I mean correct for PBC, use the nearest image convention, calculate dr, the distance between two particles, and basically if dr is less than RC, right, only then you can calculate x hat, y hat, z hat, which is nothing but dx by r. You have already corrected for the correct sign of ds using the nearest image convention. Then y hat is the basically y cap, which is the unit vector, x hat, y hat, and z hat is the unit vector, and this is how you calculate that. And this vector basically points from I to p, right. So, this is a schematic diagram. You are 3 p minus 2 to 3 I minus 2. So, the vector is pointing from I to p. We have discussed this in one of the previous classes. If you are confused, please go back and have a look there. So, you calculate the unit vectors, then you calculate the magnitude of the force. You have r, if r is less than R c, then you calculate the magnitude of the force, and then the expression of the potential. We have discussed all of this, and then the total force acting on particle number I, the x component 3 into p minus 2 is the x component, equal to total force which has already been acted upon maybe by other particles, plus force into x hat, right. And what is the force acting on the ith particle? So, you will write taut force into 3 into I minus 2, the 3 I minus 2 stores the forces acting on particle I due to other particles, minus here it was plus, here it is minus, because equal and opposite. If the force acting on P, and now you are calculating the force acting on I, which will be in opposite direction, minus force x hat, right, and that is all that is there to it. And then of course, this loop, this loop is basically ends here, you have an undo and you have an undo, and that is the standard thing, right. That is all that is there to calculation of forces and using the neighbor list. And now you will see quite around 10 times faster or 10-20 times faster than your previous molecular dynamics code. To end this class, I want to tell you I really taught you the most simplest neighbor list. The actual neighbor lists which are used in molecular dynamics calculations are much more advanced version of this. But in this course we are not trying to make you an expert of molecular dynamics, right. We are just trying we are teaching you 5 or 6 different methods, computational methods, so that you have an exposure to different types of calculation techniques, and through this you are learning how to develop algorithms, which is our main focus, right. So, for molecular dynamics you need to do such checks with the periodic boundary condition. How do you implement that? Then we discussed about thermostat, how do you implement that, cutting of forces, how do you implement that, what is the logic, and here we discuss neighbor list. This is the simplest one. If you really have to do neighbor molecular dynamics for your research or for whatever company job that you do, then of course you will have more advanced techniques which you can learn from the book, and then just like here you are going to slowly develop the algorithm. You will be able, I hope that you will be able to do that, right. Here we discuss the algorithm, the implementation, the logic in great detail. Okay, with this we will come to the end of this class, and discussion shall go on to the next class. Thank you.